going through and they had like all the eyes and you could see the handle.
This is kind of where we left off the last time we talked about some new map. And this is something that's true about any element of SN. It can be written uniquely as a product of transpositions. And this is sort of the output of the exercises that we always seem to be doing. And it can also be written as a product of transpositions. So let me show you both, if you will. So we do these kind of problems here. You can think of this as an element of S. It's an element of S8, so actually it's an element of S9 and S10 and S anything, but I've used at least 8 of the numbers, I guess, right? So we'll see what this is. Where does 1 go? X. I agree. 1 goes to 3 and then to 5 and 6. Where does 6 go? 3 to 5. 5 goes to 7. I don't know, 7. What? 7 goes to 1, to 2, to 3, to 1, to 6, to 1. Everybody agree with that assessment of the situation? What's the first number that's used up here somewhere that I haven't accounted for? 2, right? We'll see what happens there. 2 goes to 1 to 5 to 1 to 2 to 1 to 2 to 3. That was quite the dance. Where does 3 go? It goes to 2, 1 to 2, 1 to 3 to 8. It's done. And how about 8? It goes to 2, 4. 4 better go to 2. See what happens with 4. Goes to 1, 2. Good. Notice, after all that mess, this is a product of 2 4 cycles, right? And they're disjoint. There's no overlap. This computation always gives you this output, product of disjoint cycles, right? This is also a product of transpositions as well. And let's write this as product of transpositions. I'll go to 6. 6 goes to, and this one right here, 4 to 8. I agree with that. Because this first blob, let's just consider this. 1 goes to 6, 6 goes to 5, 5 goes to 7, and 7 goes to 1. So what I've done is I've broken this thing down into these 3 right here. And I've broken this one down into these 3 right here. Now notice uniqueness we don't have. If you want to say a product of transpositions, let me see if I see why there's more than one way to write this as a product of transpositions. This is totally slimy of me, but what a dork I am. I just tagged on 4 pairs of switch, 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 switch. That's an even number of switches up back to where I started. So now I can write this thing as the product of these 6 red or I could tack on this, right? And there's many ways that I can make this not unique. I could put a pair of 2 3s in between here, for example. Everybody agree with that? So here, everybody thinks it's a product of transpositions, but it may not be unique, right? But the last thing we defined is this notion of odd. So we say sigma in Sn is odd if sigma can be written as a product of an odd number of compositions. And sigma is even if sigma is an even product. I think this is the last thing we define. Now, let me point out that this one right here can be written as these 1, 2, 3, 4, 5, 6 red transpositions, right? When I gave you an example and pointed out that this was not unique, notice that I then wrote it as 10 transpositions, right? Still even. I also said, well, you could also pick a pair of 2 3s in between here, right? Still even, right? But the question remains, does this definition make sense, right? Or is it well defined in the sense that if I give you an odd, is it possible for an element of Sn to be both even and odd, right? Is there some transposition, or I'm sorry, some permutation in Sn out there somewhere in the depths of some Stephen King novel so horrifying that you can write it one way as a product of 100 transpositions and another way as a product of 237 transpositions? Can this ever be done? It's not clear that the answer to this is no. As a matter of fact, it can't. Odd, once odd, always odd, once even, always even. And we're actually going to prove this. That is, unless somebody wants to. Does anybody see an obvious proof of that? I myself have never seen anything short of that. So let me give you this theorem. So let's tackle this problem. Theorem. No sigma in Sn is both even and odd. So there is no such animal out. Okay. Any ideas on how we might try to tackle this? Any ideas?
Assume they can be both even and odd.
I think that's a good strategy. So Lily's strategy is this: assume that you can. Assume that you find something out there that can be written as a product of an odd number of transpositions and also an even number of transpositions. So we're going to give that a whirl and see what shakes out here. Proof. Suppose there exists sigma in Sn that is both even and odd. What does that mean? That means I can write sigma these are my notation here. These are going to be transpositions. So I am going to write the sigma here can be written as this product of transpositions in this product of transpositions, where each tau I and tornado J are transpositions. So they're just little two cycles, right? Okay, so assume that we can find some sigma, and I can write it as both an odd product of transpositions and an even product of transpositions. This is kind of a bit of a convenience here. Can anybody tell me what the inverse of a transposition is? Itself. That's exactly right. A transposition means just to swap two things. How do you fix that? You just unswap the other thing. Just do it again, right? So I'm going to massage this a little bit. So what did I do? I multiply on the left by tau 1, and tau 1 is its own inverse. So that breaks me down to tau 2 up to tau n, and then it puts tau 1 over here. Do it again. Right? Yes.
Silly question. You say S sub n, then you also have tau sub 2n. Are those the same n? Or they be different?
Oh, yeah. It'll be easier for me to do this here. Yeah,
Okay.
right. I'm going to continue this process of trying to, basically what I'm doing is I'm just thinking my moving man, and I'm moving these towels over to the other side step by step. And eventually I get the identity is tau 2n, tau 2n minus 1, tau 2, tau 1, tornado 1, tornado 2, left tornado 2m plus 1. Everybody agree with that? How many permutation, or I'm sorry, how many transpositions do I have on the right side of this equation? How many transpositions do I have?
9 plus 2 plus 1.
2n plus 2m plus 1, right? Everybody okay with that? And I don't know much, but I know this is odd. Everybody agree with it? Okay, this is the first what I would call a reduction of my problem, right? I started with Willie's suggestion that, okay, so write something that's both an even and an odd. And then I massaged it a little bit. And the conclusion that I've come to is now I can write the identity as an odd product of transpositions. So in other words, the identity is odd, right? By the way, I also know the identity is even because it can be written as 0 transpositions, right? It can also be written as 1, 2, 1, 2, right? Everybody agree with that? So E is also odd. Okay, so I've taken this first thing and I've said, okay, if there is out there some sigma that can be written as an odd product and an even product of transpositions, then it must be the case that the identity is an odd is an odd product of transpositions, right? And this is where I want to try to really go for the computation. So my notation here. So let K be minimal. such that the identity is an odd product of transposition. So, right, the identity is tau one, tau two, up to tau two K plus one. Okay, so would you agree? Would everybody agree? So this is basically induction. Although it may not sound like this, if you look at it closely, what we're doing is we're trying to find a minimal element in subset of the natural numbers. Suppose the identity can be written as an odd product of transpositions, right? There must be a smallest number of odd transpositions that you can write the identity as. Everybody agree with that? And can somebody name an odd product of transpositions that for sure the identity cannot be? The identity cannot be one transposition. Everybody agree with that? There's no way. That I know. There's no way the identity can be a single transposition, right? Because what this means is A goes to B and B goes to A, right? And so the identity takes A to A, this thing takes A to B. Game over, man. Everybody agree with that? But even with three transpositions, it starts to get a little murky, right? What if I had A, B, C, D, E, F, where I've got complete freedom on how to choose C, D, E, and F? It's not so clear that you couldn't muck around a little bit and make A go back to itself, right? You could sit down and do a formal proof of it, but you would find that it's surprisingly a pain a la butt to do this, right? But one is clear. Everybody agree with that? So I guess I can conclude over here, the K should be at least one. You're going to have to be, so the smallest number of transpositions would have to be probably at least three. Everybody agree with that? And of course, if I get you up to 101 transpositions, it's very murky. So how are we going to prove this? I know it can't be a single transposition. Let's suppose that this is the smallest number of odd product transpositions that can be the identity, right? And I'm going to show that I can make it smaller, right? But first, I'm going to have to give you some rules. And you guys can help me do these rules here. So what I'm going to do is I am going to move a transposition across other ones. Let me write down a couple of these rules, and I think you'll kind of catch on to what I'm doing. If I have two transpositions next to each other and they're both the same transposition, what's a shortcut way to write this? The identity. Okay, so that's my first rule that I want to pay attention to. Number two, if I have ACAB, okay, this first one, they're exactly alike. In this one, I have A in common, right? Well, this one is A goes to B, B goes to C, and C goes to A. Everybody agree with that? And I'm going to rewrite this as AB, BC. Let me check this. A goes to B, B goes to C, and C goes to B and back to A. Everybody agree with me? So what this means is, if AB encounters an AB, then they cancel. If AB encounters AC, I can pull that AB through and leave a BC here, right? Right, okay with it? Here's another one. AB, BC. Well, this one is A goes to B, B goes to C, C goes to A. Oh, A, B. Oh, I'm sorry. Let me do this one over. I did this wrong thing. I want to do, yeah, BCAB. This one is ACB. Right? And it's also equal to ACBC. Because, see, in this one, A goes to C, C goes to B, and B goes to C. And finally, I'm not gonna do anything fancy here. By the way, what's common? Forget the first one where they canceled out. Does anybody see kind of what the common theme is of these? What this might be?
Will always become a different unit transfers.
This is a way that I'm trying to figure out how to turn these things around in a certain sense. Notice that in all three of these end game, I'll copy this again, A, B, C, D. In the end game, the A survives, right? You've got an A on the train coming in and an A on the train coming out. Do I agree with that? So when AB meets AC, so when there's a match on the A, then it's AB, BC, but there's still an A, right? When AB meets BC this way, I can turn them around, and now it's AC, so I've lost the B, but I've still got the A. Everybody agree with that? And when AB, CD, then it just pristinely, you've still got the AB here, it turns around. Everybody okay with that? So this is the key to what we're going to do here. I'm going to key on this right here. So I'm going to let tau 2k plus 1 well, let me break this down again. T identity tau 1, tau 2, tau 2k, tau 2k plus 1. And I'm going to let tau 2k plus 1 equal A, B. Yes.
For the third rule, how did you get it going from A to C to B again?
Well, just from here to here, A goes to B and then to C, so A goes to C,
Okay.
right? C goes to B, there we go, and B goes to A. So,
Okay.
are you okay now?
Yeah.
Yes.
Can we do that for number 2 as well?
Yes. For this one, A goes to B, and B goes to A, and then on to C, and then C goes to A. that okay? Now, I'm gonna let this be AB. Now I am going to do this thing. Move AB step by step to the left. Right? So in other words, in the first step, I will go to I'm gonna plot these out, right? Using whichever one of these rules applies. Everybody okay with it? So if this is AB, if this is the form AC, then I will use rule 2. If this is in the form BC, I will use rule 3. And if this is completely disjoint from this, I'll just swap them. Everybody agree with that? Let's assume I never have to use the one where I encounter an exact pair. Everybody okay with that? So assume that I can just do this. As I keep flopping this one here, I never encounter something to its left that's exactly right. So I have to keep using rules 2 through 3. Then what do I end up with? I end up with tau 2k plus 1 hat, tau 1 hat, tau 2 hat, tau 2k hat. Tau 2k, well, let me actually, instead of hat, I'll use these ones in the prime because they're the same ones. Tau 2k is the end result that I got of doing that first flip here, 2k prime. Tau 2k minus 1 prime is the second flip. And this one might have changed a bunch of times, right? But everybody agreed that what we still have is a product of 2k plus 1 transpositions, right? Because nothing, I just swap things out and I've still got perhaps a different product of transpositions, right? I agree with that. Let me make the following observation. If I never used rule 1, notice that I always have an A in the left transposition, right? So when I'm done, this tau 2k plus 1 has an A here. Everybody agree with that? And tau I prime has no A. Right? Because look what's left in the wake when I flip. No A, no A, no A. Everybody agree with that? When I have the A going in, what's left in the wake, what's left at the right when it goes through, no A, no A, no A. Everybody agree with it? Yes.
I understand like the reasoning behind never using rule 1, but why are we allowed to just not have to use that
We're gonna have to use it. And that's the
one?
point.
Okay.
Let's assume that this can be done. And we do this, and I never encounter the same thing, so I can just keep doing it. I come out with 2k plus 1 transpositions. This one has an A in it. None of these have an A in it, right? This means this product of transpositions. A to X. Everybody agree with that? Because just imagine reading this. This one is form AX right here. And this is a bunch of crap that has no X's in it, or I'm sorry, no A's in it. Everybody agree with that? So when I'm doing that computation, where does A go? It goes to X. And there's no cure for that. Everybody agree with that? So, not identity. It can't be because it took A to X. Everybody agree with that? Everybody understand where we are so far? And this is where Lily's point comes in. That means we can't do this without using rule 1. It's impossible, right? Because if we get a contradiction here, because this is supposed to be the identity, but it takes A to X. So we must have used rule 1. We had to. But this means we must to had to use at least once. Right? And does anybody see what the problem is now?
Why you're still left with product of transversals in the form 2k plus 1, which becomes 2k minus 1.
This means that E is an odd product of transpositions. With less than 2k plus 1 elements of the product. And this is a contradiction. Because at the outset, we assumed that that odd product of 2k plus 1 is the smallest number of odd products that you can do. And notice that when you use rule 1, it cancels in a pair. So that drops it. Every time you do that, it drops it by an even number. So now you've got a smaller odd number product of transposition of the identity, and that's a contradiction. So that does the theorem. There is no such thing as something that is both even and odd. This is well defined. Okay. Questions? Okay, so any questions? All right, I'm going to get you another important group out of this. This allows the following. Let me build a homomorphism for you. By the way, let me ask you this. It's kind of a warm up into this theorem. So I'm going to do this a slight twist on what I did. So odd and even, well defined. What happens if I take two even? So suppose I have sigma 1 and sigma 2, and they're both even permutations. What happens when I multiply them together? What kind of permutation do I get? Still even, right? Everybody agree with that? What happens if I take an even permutation and an odd permutation, multiply them together? What do I get? What happens if I take two odds and multiply them together? I get considered into C mod 2. phi of sigma is equal to 0 bar if sigma is even and 1 bar. You all just convinced me that this is a homomorphism. Why is this? Because, for example, why is this true? Because if these are both even, then an even times an even is an even, so that should be 0 bar, and this is 0 bar and 0 bar. That works. If one of these is even and one of these is odd, this should be an odd, so this should be a 1 bar. And over here, I get 0 bar, 1 bar, right? If both of these are odd, 1 bar. If both of these are odd, this is an odd, so phi of that product should give me a 0 bar, and this phi of 1 bar, phi of 1 bar. So this is a homomorphism. Everybody agree with it? Yes.
Reason you chose to add them?
Yes, because the addition in Z, this is addition in Z2. Questions on that? So, would you also agree this is also onto? Right? The identity goes to 0 bar, the identity permutation, and I don't know, the permutation 1, 2 goes to 1 bar. If I agree with that? So this is onto. So by the first isomorphism theorem, that Sn modulo the kernel of phi is isomorphic to the image of phi, which is Z2. What is the kernel of phi? That is correct. It is the set of sigma and Sn such that sigma is even. It's a set of even permutations. And this shows that the set of even permutations is a subgroup. Multiply two even permutation, the inverse of an even permutation is even, but just appearing in the first isomorphism theorem, it is the kernel of phi. So not only is it a subgroup, there's also another very sexy adjective that I can attach to it. It's not just a subgroup, it is normal, right? Because it's the kernel of some homomorphism. It has to be normal. This has a special name, the kernel of some homomorphism, and it's called A5, or A5. It's called AN. It's the alternating group on n letters. So I'm going to put this in theorem form, probably. Well, let's see. AN is the set of sigma in Sn such that sigma is even. Theorem. AN is a normal group, normal subgroup of Sn. So not just a subgroup, it's a normal group. Here for all n greater than or equal to 2. And additionally, by the way, how big is AN? That's right. It's half of Sn, as you might expect. The even permutation versus the odd. This also follows from the first isomorphism. Okay. Any questions on that? Yes.
Back toward the beginning of class, you said that if we had some even function, we could write it as a new even function by just adding pairs of the same transversal. How is Sn finite then? Does Sn have the caveat that it's in the simplest form?
Well, so what you're doing is you add on a finite number of functions, but yeah, that's right. The reason it's finite is when you can write it in a product disjoint cycles, there's only so many ways to do that, right? Because when I did that kind of dirty trick where I put the 1, 2, 1, 2, 1, 2, 1, 2 like that, that's very redundant. And basically what I'm doing is I'm just repeating the same function 4 times in a row and it cancels itself out, right? That doesn't change the number of elements in the group.
In what situations are we considering that a unique function? And in what situations is it not?
Oh, with transpositions, you're going to get in all kinds of troubles worrying about uniqueness, right? Because in fact, I rewrote that in a cheap way, but there's usually very many ways to do something, right? Like the identity is 1, 2, 1, 2. Or I could do that 4 times or 6 times, but I could do this too. I mean, I could do 1, 2, 1, 2, 2, 3, 2, 2, 3, 5, 4, 7, 2, 3, 2, 3, 7, 1, 2, 3, 5, I think, something like this. I think this works. That cancels, that cancels. That cancels, that cancels. 2, 4, 6, 8, 10, 12. Yeah. So this cancels, this cancels. Cancels, that cancels, that cancels. Yeah, I think that's right. But anyway, maybe you get my point. This doesn't look like the identity at all, but if you start pulling this apart, that cancels, and then this cancels this because you've got that accordion in there, and then the 2 3s cancel here, and then the 4 7s cancel here, and the 1 2s cancel here, and then you got the 3 5 3 5. Right. So there's lots of different ways you can do it, and that's just a long way to write the identity. But again, it's still even, right? Because there were 12 things that I put in that little, dance around the maypole. Any questions on that? I have the feeling I didn't address what you were looking for.
How is that still a unique way to write it?
It's not. That's the point. With transpositions, you don't have a unique way to write things. If the cycles are disjoint, then you're good to go. But look at my cycles here. They're far from disjoint, right? There's lots of overlap.
But in the sense that, how is that a valid way to write that?
Well, it's valid just because it works. I mean, if you go through and check everything, where does 3 go? It goes to 5 and then back to 3. Okay, where does 2 go? It goes to 3, back to 2, then to 1, and then to 2, right? And so forth.
So when you're writing some function as a product of transversals, transpositions, there is going to be one unique way to write it in its simplest form, and any other way is just adding some form of the identity.
Oh, okay. So for sure that will be true in the following sense. If you take an element, any element in Sn, you can write it as a product of transpositions, right? Is there a unique way to write that as a shortest product of transpositions? So for sure there should be a shortest way to write it, right? Everybody agree with that? Because all you have to do, it's either even or odd, and it's just look at all the possibilities. It's whatever the smallest. If it's odd, it's the smallest number of odd transpositions you write it as. It's even, it's the smallest. Now, uniqueness let me think about that. As a product of transpositions. Okay, and I'll tell you, let me give you an example here. Well, I'll give you a concrete example. Oh, and this is kind of a nice thing to put in your tool bag too. If you ever have an odd cycle, it's even, right? An odd cycle can be written as an even number of transits. If you have an even cycle, so if you go cycle with an even number of things, it's odd. Let me give you a particular example. Here's an even transposition. Not transposition. This is an even permutation because it's an odd cycle, right? Now, I can write this. By the way, it's even. You can hear me now and believe me later because I'm going to show you. But this is an even. There's no way I can write this as zero transpositions, right? Because it's clearly not the identity. Everybody agree with that? So the best I can hope for is 2. And I can do 2 here. So 2 goes to 3, 3 goes to 1, 3 goes to 1, 1 goes to, yep. Agree? Three. Well, spell it. 2, 3. 3, 2. 2 is as short as it goes for this one, right? Because you can't go 0. And it's not unique, right? Because I can write it this way and I can write it this way, right? So I don't expect there to be a unique way to write it. There's certainly a shortest length. So if I walk up to you on the street and give you a permutation, there's a shortest length of transpositions that you could do. That's for sure. But you don't expect it to be unique because here the shortest length is 2 and there's 2 different ways to do it. Okay, that was a good question. Any other? Yes.
Is the shortest length always going to be the order plus 1 over 2?
The order
of the cycle. So in this case, that would be 3.
the cycle,
Yeah.
if you have a cycle, then it's probably going to be n-1, right? So for example, if I have the cycle, a longer one, n-1, n, this is equal to cycle 1n, 1, n-1, 1, 4, 1, 3. I suspect that for a cycle, it'll be n-1. Okay, others. Okay, I think this is probably wore you out enough today. We are going to be starting on group actions on Wednesday. So look over, we've talked a little bit about the group actions and some of the examples beginning have gone over. Familiarize yourself with that and we'll get back to it with. I'll have a good one.
Yeah, I can.